Good morning to one and all. So this is Jai Krishna, and in this video lecture we are going to discuss about stability and RH criteria in control systems engineering. So these are the topics which we are going to focus: the concept of stability, Routh stability criterion, stability and conditional stability, and we will see all the cases of RH criteria. So what is stability? Stability is a property of a system using which we can predict its characteristic for a specific kind of input. So stability basically is defined something like a system is called a stable system if it produces a bounded output for a bounded input. So bounded input means an input which is not unbounded, truly speaking. So not unbounded means it is not bounded between two levels. So a bounded signal means a signal which is bounded between two levels. Okay, so if we are giving such an input to a system, if it is producing such a kind of signal, that is another bounded signal is produced as output, so in that case we call that particular system as stable system. So a system is called stable if it is producing bounded input for bounded input. Okay, and such a system may not guarantee a bounded output for unbounded input. Okay, so when a system is given a bounded input, it must produce a bounded output. Okay, then only then that particular system is a stable system. So types of systems based on stability. So there are three kinds: absolutely stable, conditionally stable and marginally stable. Absolute stable system, say a system is absolutely stable if it is stable for any condition, for any physical parameter, for any cases. Okay, whereas conditional stable system means it is stable only for certain values of system components. Okay, so in such a case that particular system is called as conditionally stable. And marginally stable, see, usually when you take a system, when you take a stable system, absolutely stable system, that time when you are giving an input, most probably that particular output will become zero as t tends to infinity. Okay, so a system has produced some output at t is equal to 0, and later on, because of the input excitation, the output may vary. Okay, for example, if the input is alternating signal, then automatically output value will vary with respect to time. Okay, that time what happens is, for stable systems, the output drags to become a zero after certain amount of time. Okay, but this marginally stable, so the output will not become zero. Output will not become zero. It will not be become zero, but it will be between two levels. Okay, so it will be between two bounded values. Okay, for example, it may become, the output may be between 0 and 1, or minus 1 and 1, which is a sinusoidal signal. Okay, if a system is producing sinusoidal output, we may treat that as marginally stable. Okay, next, definitions of stability. So there are different definitions. Let's see the first one. A system is stable if its output is bounded for any bounded input. That is what we have seen. The second one, a system is asymptotically stable if in the absence of input the output tends to 0 irrespective of initial conditions. See, it means when there is no input, okay, when there is no excitation, the output must be a 0. Okay, that is another condition. And a system is stable if for a bounded disturbing input the output vanishes ultimately as t approaches infinity. Okay, so this is one particular case. So when you are defining the output to be a bounded, so it need not be a bounded. If it is becoming a 0, then also it is a stable system. Likewise, we have different kinds of definitions. The next one, see here. So here in this particular slide, what we are thinking is we are thinking further on stability. Let's take a system. Let's take a system defined by its transfer function m of s, which is given by a by s plus a. Okay, a by s plus a. So what is the pole for that particular system? How to calculate pole? How to calculate pole? So the denominator polynomial, we will make it equal to 0. Okay. So for that particular case, what is the value of a? What is the value of s? So here s plus a is the denominator polynomial. Let us make it equal to 0. That time s becomes minus a. Okay. So the pole is plotted in that particular figure, and in the right side the time domain version is given. Okay. So what is m of t? So m of s is 1 by s plus a, then m of t becomes a into e power minus at. Okay, that time the response is plotted. You observe that response. So at t is equal to 0, the value of the signal is a, and as t increases, the output is falling down exponentially. Okay. Similarly, for the next case, see here m of s is a by s minus a. Okay, that time pole is plus a, and m of t is a into e power plus at. That time the output is plotted. See, you can see when t is equal to 0, the output is a, but as t increases, the output is increasing exponentially. Okay, the next one. See here, we have taken complex conjugates as the poles. So m of s is a by s plus a plus jb plus a by s plus a minus jb. Okay, so the roots are a plus or minus jb. So these minus a plus or minus jb. So in that particular case, the poles are given, as well as m of t is calculated to be 2 into a e power minus at sine function. Okay, and you can see the plot. So it is a sinusoidal signal, but exponentially dragging to become a 0. Similarly, the next example, you can see that there are two complex conjugate poles and the real value is positive. Okay, so in that particular case, the m of t is also given, which is 2a e power at cos function. So in this particular case, again it is a sinusoidal signal, but exponentially increasing. Okay, so now one more example. Here there is no real part. We have taken pair of roots which are on the imaginary axis. So m of s is a by s plus jb plus a by s minus jb. Okay, so the roots are plus or minus jb. That time we got pure sinusoidal function, and it is plotted in time domain. See one more example. So in the previous case, we have taken complex conjugate roots, but only one root at one place, but we have taken double roots in this particular example. That time we will be getting m of t as 2at cos function. Okay, that time we are getting a cos, but it is multiplied by t. So as t increases, the function will be increasing. So one more example, m of s is a by s. In this particular case, the pole is s is equal to 0. Okay, pole is s is equal to 0. So the pole is given there, and time domain function is a into u of t. The function is plotted. Okay, similarly here in this example, we have taken double poles. Previously just a by s, so s is equal to 0 is the pole, but now a by s square, so we got s is equal to 0 and one more s is equal to 0. So two poles are there, and that time m of t is simply at. So it is purely increasing. Okay, see, we have taken different example. I will repeat the first one. So in the first case, the poles are on left side of imaginary axis. That time the output you observe, it is falling down. But in the next case, the pole is on right side of the imaginary axis, that time the output is increasing. So in the first case it is stable, the second case it is unstable. Okay, and let's go further. The third you can observe, that is stable, and next one is unstable. So there is a correlation between the location of pole and its stability. Okay, see, I have given multiple examples not to confuse you but to identify a point, that is the relation between the stability and location of poles. Okay, if the poles are on a specific location in that xy plane, that real and complex plane, we can say something about the stability of the system. Okay, that's why we have taken this many examples. Now you see the remaining. So in this particular case, the poles are on the imaginary axis. Okay, that time we got marginally stable, yes or no? So it is not falling down to zero or it is not rising. The output is between two levels, so it is marginally stable. Okay, one more example here. The poles are on imaginary axis but double poles are there, that time we got unstable output. And here again, so the pole is on the imaginary axis as well as on the real axis, yes or no? So because it is s is equal to 0, so that time we got marginally stable. But when there are double pole at s is equal to 0, we got unstable system. Okay, so we can state something like, if the poles are lying left side of the imaginary axis, that time we will be getting stable system. Similarly, if the poles are on right side, then undoubtedly it is an unstable system. Okay, but if the poles are lying on the imaginary axis, and if it is not multiple pole, okay, if there are single poles which are lying on the imaginary axis, they may become complex conjugate. Okay, but the system is marginally stable. If there are multiple poles which are lying on imaginary axis, then the system becomes unstable. Okay, so keep all these things in your mind. Then going further, RH criteria. See, to calculate or to identify the stability of a system, so this is the first technique proposed back to 1895. Routh proposed this particular mechanism in 1876, and RH proposed independently in 1895 in a different pattern, but both are very similar. Okay, the concept behind these two criterions are similar, but Routh mechanism is found to be easy as well as accurate. So by combining these two, this particular concept is presented here. So how to calculate, how to know the stability of a system, okay, using RH criteria. So that is the thing now. So first of all, what we will be doing is, we are going to take the characteristic equation of a system. So what is the characteristic equation? The transfer function will be there. Okay, so the denominator of the transfer function will be there. You take that particular polynomial, make it equal to 0, that will form characteristic equation. Okay, in that particular characteristic equation, for example, you have an s power n plus an minus 1 s power n minus 2 s power n minus 1 plus an minus 2 s power n minus 2 and so on. Okay, if you have that particular characteristic equation, then we will be forming a Routh table, something like this. Okay, so here we are going to take alternative coefficients, and we will be writing the first row. You observe lambda power n. For that particular row, we are taking an minus 2, an minus 4 and so on. Similarly, the next row will also be written directly from the characteristic equation. See, remember, the first two rows will be filled directly from the characteristic equation. The remaining rows we will be calculating using the above two rows. We will see how. Okay, by taking few example. Directly I am going there. Yeah, you observe here, the first two rows are already written. Okay, something like x0, x1, x2, x3 and so on. Similarly, the next row is also written y0, y1, y2, y3 and so on. Okay. Now, then another row, the next row z0, z1, z2, z3 and z4 we are going to write using the above two rows. How means, you see z0 is calculated by calculating the determinant of x0, x1, y0, y1 and then we are dividing by minus y0, or we can write something like minus 1 into determinant of that x0, x1, y0, y1 divided by y0. Similarly, z1, the next value in that particular row is calculated using, you see, the determinant x0, x2, x0, x2, y0, y2 divided by the same y0. Okay. Similarly, the remaining. So this is how we calculate. We will take an example for better understanding. Yeah, they say this is something like a revision. Yeah, let's see this example. See, the characteristic equation is s power 4 plus 2s square plus 2s cube plus 6s square plus 4s plus 1 equal to 0. So the highest order is 4. So s power 4, s power 3. These rows will be written directly from the characteristic equation. So how? For s power 4, the coefficient is 1. Then we have 2s cube will be writing alternatively. So we are not writing. Then 6s square is there. So write that 6 and 4s we are not writing. Write 1. Okay, so the first row becomes 1, 6, 1. Then for s power 3, go to the characteristic equation, write the coefficient of s cube. What is coefficient of s cube? 2. So we will be writing the 2 and alternative. Then 4 is there. So we will write 4 and then there is nothing. So we are not going to write anything. So first of all, we will be having only s power 4 and s power 3 rows. Now we have to calculate the values for s square row. Okay, for that what we will be doing is, see, you observe s square row, they have given that is b1 is equal to minus 1 by 2. Minus 1 by 2 is 2 is from s power 3 row, that beginning 2 we have written, and then determinant 1624, that particular determinant value will be calculating. So we will be getting b1. So b1 is calculated to be 4 here. And coming to c1, so which is the second coefficient in s square row. So here how we are calculating? So minus, see, you observe 2 and 4. No, see here what was done is c1, they are trying to calculate c1 which is in the next row. Okay, they are filling first row, first column. Okay, so c1 they are trying to calculate. So how to calculate c1? c1 is 1 by 4. Okay, and determinant of 2, 4, 4, 1. Actually, before calculating c1, we have to calculate b2 also, which is 1 here in the s square row. You observe after 4 there is a 1, yes or no? So how to calculate that one? So determinant of you see 1, 4, 1, 2, 1, 0 is there. See, in the top two rows, 1, 6, 1 is there, 2, 1 is there. So to calculate the first coefficient in the s square row, we have taken the determinant 1, 2, 1, 6, 2, 4 and divided by minus 2. Similarly, we have to take the determinant of 1, 1, 2, 0, okay, and divide it by minus 2. So that will give you 1. That is what they have written. It is written directly. We have few more examples there. We can see how to calculate those values. And c1 is calculated. So this is how to actually fill the Routh table. Okay. After filling Routh table, we will be determining the stability of this particular system. See, and we will see how. Okay, for better understanding, let's take this example also. Okay, for just calculating for on how to fill the Routh table. Okay, let's consider this example also. So here T of S is given. The characteristic equation we have, that is s power 4 plus 2s power 4 s power 5 plus 2s power 4 plus 3s cube plus 6s square plus 5s plus 3. Okay, so s power 5 column we are writing directly from the characteristic equation, which is 1, which is the coefficient of s power 5, then 3, which is the coefficient of s power 3, then 5, which is the coefficient of s. We are writing alternatively. Similarly, s power 4, so 2, 6, 3. Okay, which are the coefficients of s power 4, s power 2 and s power 0, which is 1. Okay, then how you are filling that particular row s3, s power 3. So we will try to understand how to calculate the terms which are written in s power 3 row, and then we will go back to the regular discussion. Okay, see here how you are calculating is 1, 3, 2, 6 is there. So let's calculate the determinant of that and divide it by minus 2. Minus 2 is, which is the coefficient at s power 4 row, the first term. Understand? Similarly, in the s power 3, the second term, how you are calculating is 1, 5, 2, 3. See, we are taking 1, 5, 2, 3. So that particular 2 by 2 matrix, and we are calculating the determinant and divide it by same minus 2, which we have used earlier. Similarly, next term, so the next term is 1, 2, 1, and after 5 there is nothing, so let's write 0. Similarly, in the s power 4 row, 2, and then after 3 there is nothing, so we will write 0. So 1, 0, 2, 0, determinant of that divided by minus 2. Okay, so this is how to fill Routh's table. So let's go back to the regular discussion. So far we have discussed how to fill Routh table. Okay, so after filling Routh table, how to determine the stability. See, let's see the Routh stability criterion. The necessary and sufficient condition for stability that is that all the elements in the first column of Routh array be positive. Okay, so and if this condition is not met, the system is unstable, and the number of sign changes in the elements of the first column of the Routh array corresponds to the number of roots of the characteristic equation, which is nothing but poles, in the right half of the S plane. Okay, so this is very clear. So after filling the Routh table, the coefficients, the terms in the first column should be positive. Okay, if there are any negative terms, then sign has changed. Okay, so we can calculate number of sign changes. That many poles will be in the right half of S plane. Okay, so Routh-Hurwitz criterion is not only defining the stability but also defining the number of poles lying in the right side of S plane. Understand? So this is the revision. So here this is the example. Let's see the same example. In this particular case, the Routh table we have derived. See, in the first column everything is positive. So the system is stable. See, in this particular RH criteria there are two special cases. Okay, actually if you properly observe, after calculating, see in the previous example also, here when you are trying to calculate the terms of S square row, you are dividing some determinant by 2. Yes or no? Similarly, when you are trying to calculate the coefficients in the S power 1 row, you need to divide some determinant by 4. Understand? And so on. So when you are trying to fill the terms in some specific rows, you need to divide some determinant by a coefficient which is in the first place in the above row. Okay, for instance, if that particular term becomes 0, what will happen? So we cannot divide by 0. Yes sir, we cannot perform a division by 0. So that is one special case. Okay, similarly another special case, if all the terms in a particular row becomes 0, what to do? Okay, so these are the two special cases, and let's see how to uh, deal these two cases. Case 1, if the first term in any row of the array is 0, while the rest of the row has at least one non-zero term, that is the case 1, special case 1. So here what we will be doing is, I will take an example and let us discuss. See, this is the example where s cube term, the first term became 0. Okay, then s square, if you try to calculate s square directly, then we cannot perform the division by 0. So that time we will be assuming that particular 0 as some small value epsilon. Okay, and just continue filling the Routh table. Okay, and after filling the Routh table, you take the first row columns, first column values like this 1 2 epsilon, that is where we got 0. So we have replaced 0 by epsilon, and then we have continued, right? So s square term is 6 epsilon minus 7 by epsilon, and s power 1 we have calculated, s cube we have calculated. Okay, now for example, epsilon is a positive value. For instance, if you take epsilon a positive value, then you can observe that s square is a negative. Okay, if epsilon is positive, small positive, epsilon is small positive, it is a 0 actually. So just a little more than 0. Okay, little more than 0, that time we will be getting 6 into that little 0.0001, so something 0 minus 7, so we will be getting a negative value. And similarly s power 1 term, it will become a positive. So there is a sign change. Yes or no? There is a sign change. How many sign changes are there? So from s cube to s square, there is one sign change, plus to minus, and again minus to plus. So there are two sign changes, which mean that there are two poles on right side of S plane. Similarly, if you take epsilon and negative value, small negative value, again there are two sign changes which corresponds to two poles in right side of S plane. Okay, so this is method 1. So in case 1, in special case 1, so to deal that special case where we are getting a 0 at the first location and there are at least one non-negative coefficient in the rest of the values in the same row, so in that particular case there are two ways to deal this. Okay, the first method we have just now taken, that is by assuming epsilon in place of 0. Okay, and the second method, so the second way, here t of s is given, so just replace s with 1 by s. Okay, replace s by 1 by s, that time d of s becomes, so first of all s power 5 is there, so we will be writing 1 by s power 5, then plus 2 by s power 4, plus 3 by s power 3, plus 6 by s power 2, plus 5 by s, plus 3. Okay, then multiply with s power 5 and make all those calculations, and the denominator, after substituting 1 by s in place of s, you will be getting 3s power 5, so this particular expression. Okay, so now you prepare the Routh table for this. Okay, you prepare Routh table for this. Now there will be no 0 term. Understand, this is how we overcome. So this is one example for regular Routh table preparation also, so you can go through this. Okay, so here also you can observe that there are two sign changes, okay, which is the same result which we obtained using the earlier method. So case 2. So in this case, we will be getting all zeros. Okay, so you can see that s power 3 row we got all zeros. Okay, when you are preparing RH table, Routh table, so we are getting all zeros. Okay, how to deal with this particular case? So see, before getting all zeros, okay, you have tried to fill the Routh table. That time you came across a condition where you are getting all zeros. Okay, just before that row, some non-zero terms are there, right? So you take that particular row. Okay, so in our case s power 4 row is there. The coefficients are 1, 6, 8. The coefficients are 1, 6, 8. See how they cancel. 7, 42, 56 means, so all three numbers are divisible by 7, so they have divided by 7. Okay, so we got 1, 6, 8 as a coefficients, and beginning term is s power 4. So we can write the equation s power 4 plus 6s square plus 8. Okay, that is the polynomial we got. Okay, p of s is s power 4 plus 6s square plus 8. Okay, now you differentiate it by s. Okay, when you differentiate, you will be getting 4s cube plus 12s plus 0. Now the column where you got all zeros, you write the coefficients from this particular polynomial. Okay, so see here, so we got zeros, so we have removed those zeros, and when you differentiate, you got 4 and 12. 4 and 12, you write 4 and 12 and one more 0, and again 4 and 12 are divisible by 4, so we will be writing 1 and 3. Understand? And then you continue, and you see there that there are no sign changes, so there are no right hand side poles. Okay, so let's take another additional example in case 2. Okay, so the characteristic equation is given, and we are trying to fill the Routh table. That time you see, when you are at s power 3 row, that is row 5, we got all zeros. Okay, so we will be going to s power 4 row, we will be writing the auxiliary polynomial, and then we will be differentiating that, and we got 4 and 2, so we can write 2 and 1, that is after dividing by 2 we will be getting 2 and 1, so write 2 and 1 in the place of s power 3 row 5. Okay, and then you continue. So again here it seems that there are some poles. See here, you observe there is a pole at s power, there is a sign change, from s power s square to s power 1, and then from s power 1 to s power 0. So there is a 0.05, then -3, then 1. Okay, so there are two sign changes, so correspondingly there are two poles which are lying on right side. See, I have taken this particular example to identify the location of all the poles. See, because there are two sign changes, we can easily say that there are two poles on right hand side of S plane. But because there is an occurrence of all zeros, it means that there are few poles on the imaginary axis. Understand? When you are getting all zeros in any row, it directly means that there are some poles on the imaginary axis. In this particular example, we are trying to identify how many poles are on the imaginary axis, and how many poles on the left side, and how many poles on the right side. Already we have calculated the number of poles which are lying on right side of S plane, because there are two sign changes. It means that there are two poles which are lying on right side of S plane. Let's see the remaining process. So now what is the auxiliary equation? Auxiliary equation is s power 4 plus s square plus 1. Okay, so we are making that equal to 0. Then we are trying to solve that. For that we are substituting x in place of s square. So we will be getting x square plus x plus 1 equal to 0. Then the roots of x becomes 1 at an angle of 120 degrees and 1 at an angle of minus 120. Okay, and this is x. And what about s? So s is plus or minus square root of x, because we have taken s square as x. Okay, now after calculating we got 4 values for s, because auxiliary equation is of order 4, so we will be getting 4 values for s. So you observe those values, plus or minus 0.5, plus you forget about that imaginary value, similarly plus or minus 0.5. So here what does it mean? So you observe, two roots of auxiliary polynomial are lying on right half of s plane and the remaining two on left half of s plane. The roots of auxiliary equation are also the roots of characteristic equation. So the two roots lying on the right half of s plane are indicated by two signs in the first column. The remaining 5 roots are C. So just before, I have made a statement that when we are getting all zeros in a particular row, that this particular condition does not guarantee that there are poles on the imaginary axis, but it guarantee that there are complex conjugates. And that may lie on the imaginary axis, but it is not mandatory. Okay, so this particular example, so here after calculating the auxiliary equation and after calculating the solutions of that particular auxiliary equation, which are directly the solutions of characteristic equation, we came to know that there are two poles which are lying on right side of that particular imaginary axis. Okay, so all the remaining are on the left side. Okay, because it is a polynomial of s power 7, so total 7 poles are there. So 2 poles are lying on right side, and all the remaining are on left side. See, when you are calculating the solutions for this auxiliary equation, you may come across the case where there are few poles which are lying on the imaginary axis. Understand? So this particular calculation, that is the solution of auxiliary equation, so this particular calculation will help us to calculate the number of poles which are lying on imaginary axis. Okay, see in the previous you go through, you see here s is plus or minus 0.5 plus j 0. Something we got, right? So for instance, if you got no real part, here you got 0.5, right? So for instance, if it is a 0, then we are sure that there are few poles which are on the imaginary axis. For instance, if they are double poles, okay, if they are double poles which are lying on the imaginary axis, that time what will happen? So even though there are no sign changes, that there is a possibility of instability. Understand? So whenever you are getting all zeros, we cannot simply ignore the solution of auxiliary equation. Okay, we will calculate the solution of auxiliary equation and we will see that there are no double poles on the imaginary axis to guarantee stability. Okay, as we have seen in the beginning discussion, when there are multiple poles on the imaginary axis, even though they are not on the right side, so the system becomes unstable. Okay, thank you for listening my lecture.